Good afternoon, everyone. So we are going to have two talks this afternoon, and remember that after that we have the reception, the wine and cheese party, which is going to happen in the room next to this room here. Okay, so let's start. It's my great pleasure to introduce Kaveh Mousavand from Queen's University, and he is going to speak about the distribution of Schur representations of finite dimensional.
I, of course, wish to begin by thanking the organizers for the opportunity, as well as the technical support. The gentleman has been working tirelessly for the past few days. If he felt unwell or we were busy, we could just give a talk, but he could not. So he has been probably working much harder than somebody like myself. So I'm very thankful to all of you. As the title suggests, I'm going to speak about the distribution of Schur representations over finite dimensional algebras. I understand the Schur representations and the concept of representation means different things to people. Of course, there are deep connections, but I want to focus on finite dimensional algebras, view representations as modules, and pick up the most common elementary language that we can adopt in order to communicate a problem without getting to too much of technicalities. I allude to the more technical aspects of the problem. In case any of those aspects is of your interest, we can certainly discuss that, but I don't want to overwhelm you with too many unfamiliar terms, so it becomes complete waste of your time. The thing I wish to do is also, I'm gonna waste a few minutes, of course, but I'm going to upload this talk to the chat box. If I want to begin talking about the problem while this gentleman assists me with uploading the PDF file to the chat box, because if I'm going too fast, which is very unlikely, then you can look at the PDF file. If I'm unclear about any matter, then the audience, online audience, can also consult the PDF file. What I'm going to talk about is technically a problem which stems from a very classical question. When you're given an algebra and we want to understand the module theory of that algebra, we better understand the indecomposables, because the Crewler-Schmitt theorem tells us if you're given a module uniquely up to permutation, decompose it into indecomposables. And then if you want to understand the entire module category, understand the indecomposables over that algebra and the morphisms between them. With that, you technically understand the entire module category. Then the question becomes, if you're given an algebra, this algebra may have finitely many indecomposables or infinitely many indecomposables. And in either case, you want some systematic ways of treating the problem. In particular, there are natural questions that arise, such as, if I have finitely many indecomposables, is there any gap between the length of indecomposable modules that I have? For example, let's assume I have 127 indecomposable modules. Do I have indecomposable at every length, let's say d, between 1 and 127? Do I have an indecomposable of length d? Or are there gaps in between? A very natural question. Then let's go. If it's not possible, we can return to the original platform and we proceed from that. If I have infinitely many indecomposables, then what phenomena could I study? For example, again, let's return back to the very simple elementary question. Do I have gaps in the length of indecomposables that I have over my algebra? If I have infinitely many indecomposables now, for any given integer you suggest, can I give you back at least one indecomposable? You become a little bit more ambitious. You say, well, you said you have infinitely many indecomposables. Can you give me back an infinite family of indecomposables of a particular length? Give you d, integer d. Is there an infinite family of indecomposables of length d? Well, this question itself is wrong, because if you give me an arbitrary integer, I likely fail to give you back an infinite family of indecomposables of that particular. Are there integers for which you get an infinite family. Then you become even more ambitious and you say, if I give you an algebra which admits infinitely many indecomposables, is there an infinite sequence of increasing integers, d1, d2, d3, such that for each of these di's, you have infinitely many indecomposables of length di. So we are just building up on the level of complexity of the problem, right? We just started from any given arbitrary finite dimensional algebra. And such problems turned out to be the center of attention for a period. Can I return to the original setting and proceed? So I have outlined some very elementary problems that can come up when you begin from an arbitrary finite dimensional algebra over an algebraically closed field. For the sake of simplicity, to avoid unnecessary reiteration of terms, I want to assume that the algebras we are working with are connected and basic. Let me explain what these words mean. Connected means the only central idempotents I have are 0 and 1 identity, multiplicative identity. Geometrically, if you want to visualize it, connected means you cannot separate your algebra into two parts such that they don't have anything with each other. Are we back to the Zoom setting? Sorry if I disturb you with this unforeseen situation, but if I could go back to the original platform, that would be great. Otherwise, I'm technically going through the slides, but verbally, as long as it doesn't require writing, because the main objective I have in this talk is not bombarding you with a bunch of like terms which are unknown and probably some results that interest myself and my collaborator only. Instead, if I could communicate the problem that you're thinking about and avoid some technicality, that would be the ultimate goal. Are we back to the perfect? Thank you very much. So we were here, and roughly speaking, oh, this is not the one that I meant to use. So sorry, I think you got it wrong, but it was my fault. I'll fix it. So roughly speaking, I want to talk about the strict versus continuous phenomenon after talking about the running idea. Henceforth, this is the outline of the talk, which I've briefly kind of covered, but I'm going to skip over that in the interest of time. But the notation and convention remains as follows. I assume K is an algebraically closed field, and NA henceforth stands for a basic connected finite dimensional algebra. If you're interested in even more simpler but equally reliable setting, assume K is the complex numbers and A is your favorite finite dimensional algebra over C. Basic means every simple A module is one dimensional, and connected means the only central idempotents are 0 and 1. You may object that, oh, you're losing generality. No, actually, if you give me any finite dimensional algebra over any algebraically closed field, we can say the same thing about that. Okay, so that said, by the notation capital mod and capital int, I respectively denote the module category of all left A modules and the set of iso classes of indecomposables. I care about modules up to isomorphism classes. Similarly, small mod A and a small mod int denote the small modules, namely those which are finitely generated. And because A itself is a finite dimensional algebra, finitely generated module over a finite dimensional algebra is finite dimensional as a vector space, right? So when I say small modules, it means like the dimension of them as a vector space is finite. This is how we visually see the module category of a given algebra. The large module category, the set of all indecomposables, the small module category, the intersection of all indecomposable with the small module category becomes the small indecomposables. So the Krull-Schmidt is the one that I alluded to earlier. And then an algebra is called representation finite if the set of small indecomposables is a finite set. So we just talked about a couple of valid questions, elementary questions we could ask about the set of small indecomposables. If it's finite, well, do we have any gap? Can we have multiple indecomposables of the same length and then somewhere a gap in between and a jump or something? And if it's rep infinite, then it becomes a little bit more complicated. You cannot just hire a graduate student and then give them a finite dimensional algebra and say, like, okay, list all the indecomposables. The graduate student cannot leave in the second year after they learn the basic of the setting. You know, so there's no chance of graduating a PhD student with a rep infinite algebra if you don't want to approach it systematically. Therefore, for rep infinite algebras, and please let me highlight the fact that I alluded to earlier, that the length is the same as the dimension, thanks to the assumption that the algebra is basic, okay? Why do I use the term length? Because these problems make sense over any arbitrary finite dimensional algebra. So length is a stronger term if you want to use it. A bunch of questions that I kind of listed are the ones that I stated earlier before I shared my slides. And if we want to do rep infinite algebras, then there are more complex questions coming up. If we have infinitely many indecomposables, is there any bound on the length of indecomposables? Can it be like we have infinitely many indecomposables, all of them pile up here, and there, like, after like 10 steps, there is no indecomposable. All of them have kind of piled up forever on top of each other. Or no matter how far we go, we still find an indecomposable. Like, what is the setting that happens in that regard? The second question is there any gap for infinitely many indecomposable representations? The one that I stated earlier. Even more ambitiously, find an integer for which there are infinitely many indecomposables piling up on each other. And the last one that I again stated, can you find an infinite sequence for which each of these DIs admits an infinitely many indecomposables? So just think about a bunch of elementary problems and see how attractive they were and how long it took for people to come across reasonable answers. They were the broad conjectures that received a lot of attention in the 50s. They were posed as homework problems to graduate students. Quote from Ringel, quoted from Brouwer that he had assigned. Oh, this quote was also mentioned in another paper. So quote by quote by quote, there were problems posed to the graduate students. Okay, homework. The first one is exactly the no bound property. That if you're working over a rep infinite algebra, there is no bound on the length of indecomposables. It cannot happen that you have infinitely many indecomposables, all of them pile up here before number D, and then there is no indecomposable after D. No, the more you go, you know, you still find indecomposables. You cannot stop somewhere and say, like, I've collected all indecomposables. No. The second thing is that infinite sequence of integers exists. These are still conjectures, okay? These are still homework problems. So students are still working on them so hard from 50s until they turned out to become theorems. One of them in 68 by Reuter, and the other one, the other homework was a little bit harder, 1984. And in between, a large group of outstanding representation theorists working on these homework problems quietly. But actually, they became the center of attention for a period, a direction of representation. People in between, when they couldn't solve the harder second Brouwer conjecture, this infinite sequence, proved a lot of outstanding mathematics in this direction, including the result of Smollett, which states if you find one integer for which you have infinitely many indecomposables of that length, you can find that desired increasing sequence such that you get D1, D2, D3, each of which admit infinitely many indecomposables of length Di. So that was an outstanding result before the second one was proved. But the no gap problem was a little bit harder, and it took a little bit more than half a century to be proved in 2010 by Bongartz that if you give me an algebra, every integer that you give me, so if your algebra is rep finite, every integer that you give me, well, if you have like m many indecomposables, there's certainly any one indecomposable for length between 1 and m. If you have infinitely many indecomposables, you can still find at least one indecomposable for every integer d. So no gap in the length of the indecomposables. Great. So now the problems for indecomposables are solved. But what was the technique? Well, they reduced the problem from rep infinite algebras to a particular type of rep infinite algebras, which are called minimal representation infinite algebras. What is the minimality with respect to? With respect to the following properties. First, notice that a minimal representation infinite algebra is evidently representation infinite, but the minimality is the following property. If you take any further quotient of that, it becomes rep finite. Okay, so your algebra is rep infinite. If you take any further quotient of that, it becomes rep finite. It sits at the very bottom of the family. So if you assume this is the family of all algebras, these are rep infinite algebras. These are rep finite algebras. Mean rep infinite algebras are living here. If you take any quotient further, you fall into the realm of rep finite. So they reduce the problem from that generality of everything here to studying this family. Okay, what did actually inspire them to focus on this family of rep infinite algebras? A relatively well-known, easy lemma, fundamental, but well-known and easy. That if you pick up any surjective map of algebras from A to B, any surjective map, then you get an exact embedding of the module category of the codomain B to the module category of the domain A. Namely, every B module can be viewed as an A module. So the picture that I always think of is like I started from that arbitrary algebra, okay, and then I focus on the module category of the codomain, which sits inside that. Everything kind of intersects nicely. As a corollary, if you want to solve any of those fundamental problems that I asked or posed after those beautiful conjectures, well, start from an arbitrary rep infinite algebra, take the quotient, and then every time you take the quotient, you fall into another algebra. But the phenomena that happens is the following. Notice that we started from that larger one, we went to this smaller one, and then we are asking the same problem or problems about this smaller module category. As long as the algebra that you're working on is still rep infinite, you can reduce the problem to B. And if you still can take a quotient and get another rep infinite algebra, go to that quotient, and finally find the one which is the smallest, the minimal with respect to rep infiniteness. So if you solve the problem for that smallest one, you can prove the results for the original algebra. That was the motivation and the technique. So that was pretty much the way that they moved from the arbitrary rep infinite to mean rep infinite. With that introduction said, if you're given a rep infinite algebra, it's again overwhelming to start thinking about it without any systematic subdivision of the family of rep infinite algebras, all of them here. As long as mathematics is concerned, in my naive way of thinking, when we have a very hard problem, it's better to divide the level of complexity to different layers. How complicated the problem is. As long as this problem is concerned, the main breakthrough of study of rep infinite algebras was due to this Ukrainian gentleman, Yuri Drozd, who proved in '79 Yes, if I got the date right. So in 79, it proved that if you pick up any rep infinite algebra, namely an algebra which admits infinitely many isoclasses of indecomposables, that algebra is either tame or wild. Namely, the level of complexity of rep infinite algebras now fell into two subfamilies, tame or wild. Before giving you an overwhelming definition, technical, let's see what is the hope of tame versus wild. What is the point in the first place? For tame algebras, roughly speaking, one can parameterize indecomposables of a given length. One can parameterize the indecomposables of a given length. For wild algebras, there is no hope to do a fancy thing like that. You cannot parameterize indecomposables of length d. But for tame, your hope is to parameterize. Now you saw this. I mean, of course, the theorem was a little bit more fundamental than having like blue and red and green boxes, right? So I assume it was a little bit more fundamental, but the picture is pretty much like that. And you see rep finite ones fall into the tame ones because you can parameterize the finite number of indecomposables. Well, good. So here now you have two subfamilies. We turned a relatively possible problem of studying infinitely many indecomposables at the same time to a more tractable setting of parameterizing them or not being able to parameterize them. So let's focus on the parameterization. The definition of tame is as follows. If it's overwhelming, don't worry. We're going to turn to a more tractable setting soon. So, but a tame algebra is the one such that for any integer d, you can find finitely many bimodules, m1, m2, m2, mn, d, that n depends on d, of course, such that these mi's are as following. Each of them viewed as a module over the polynomial ring is free of rank d. D is the integer that you fixed from it. Furthermore, so what is the significance of these mi's? So far, nothing. Like these are free bimodules, free over the ring of polynomials of rank d, okay? But the way that they contribute to the parameterization is as following. If you pick up any indecomposable of your original algebra A, any, you can write it in the format of this tensor product with one of these mi's. Okay, that is the precise definition of tameness. Is that the way that I usually think about it? Every time that I want to check whether or not an algebra is tame, I would go and search for, like, I pick up an arbitrary d and I said search for like n many bimodules and check their free rank of d. No, this is not the way. So there is, of course, after proving such a fundamental breakthrough, there are still attempts to give other realizations of tame versus wild. What are those? Those are the ones that I want to describe. But let me give you an example of rep finite, rep infinite, both tame and wild. They are not that wild, actually. That wild are wild, but they don't look that wild. Rep finite, the path algebra of this quiver with two vertices and one arrow. What do I mean by path algebra? Generate the algebra for which the generators are the idempotent at vertex 1, idempotent at vertex 2, and this alpha, okay? Multiply them. What are the relations? E1, E2 becomes 0, E2, E1 becomes 0, EI squared becomes EI. These are lazy paths. And then whether the composition is possible, and like very, very natural construction of path algebras. Okay, this is rep finite. How many indecomposable does it have? You may wonder. Okay, it's pretty easy. So we just added one arrow. Then it's like, again, construct the path algebra of this. What are the generators for this? E1, E2, alpha, and beta. What are the relations? Similar relations. Whenever composition is possible, compose them. Whenever it's not, 0. How many indecomposable does it have? Infinitely many. What are those? I'm not going to list them. We add one more arrow. Again, path algebra with the generators E1, E2, alpha, beta, gamma. How many generators do we have? 1, 2, 3, 4, 5. Okay. Set of relations are similar to this. How many indecomposables do we have? Infinitely many, but in which sense? In the sense of wildness. Namely, if you pick up certain integers, there is no way you can parameterize indecomposables of this algebra of that length. Question?
Are you going to give a definition of wild?
No.
And it's not being tame, right?
Exactly. No. It can be defined very like rigorously. If you want just an allusion to that, it's a functorial definition, which technically says an algebra is wild if you can find a full, faithful embedding of this algebra. Okay, which is, if it's wild, you can embed the module category of this algebra into the module category of that, if this is wild. Okay.
But the first one is mod k xy, right?
Oh, sorry, of course. Thank you. Mod k xy.
And the angle brackets mean that generators don't create, right?
Yes, yeah, exactly. That's the functorial definition of wildness. So if it's wild, you can technically embed any arbitrary module category of any algebra into your given module category. If A is wild, that is what it means. This is how you should view wildness. It's really wild, but it doesn't look so. Okay, I'm short of time. Here is the example. Now I'm going to give you another incarnation of tameness, equivalent condition, which in my opinion is more general. Of course, it's not my opinion. That's like the fact. It's more general. My opinion is more tractable. Before giving you the definition, recall that if you're given a module, you can construct the endomorphism algebra of that module, right? It's an algebra. Obviously, your module M is a module over its endomorphism algebra, the second trivial observation, okay? And then because M is a module over its endomorphism algebra, you can ask about the length of M over this particular algebra, right? We call this length endo length because now M as an A module has a length over A, and as an end M module has a length over endomorphism algebra of M, okay? So simple observations that we have learned in like basic module theory that we can construct endomorphism algebras. Then a module is called generic. You'll soon see why. It's called generic if it's, first of all, it's an indecomposable of infinite length over A. So where does that live? It lives here, not in the finite dimension setting. Generic must be an indecomposable of infinite length over A, but of finite length over its own endomorphism algebra. Namely, it's endo-finite, namely, and the length over the endomorphism algebra is finite. So the first question is whether or not such modules exist, right? That's a very natural question. When we define something, we want to make sure that we have not defined something ridiculous, or people cannot really catch us if something is very ridiculous immediately. So generic modules, do they exist? That's a question. And what are their properties? Their properties are those. I'm not going to discuss existence of generic modules as such. That's something which has been done very neatly by Crowley, Bovey, Ringel, and many others. I'm gonna use the definition to say that, okay, generic modules are sitting over there pictorially. And you want examples? Here is examples over this algebra, which was tame. One of them, this one is non-generic for a reason that I can explain if you ask afterwards. This one is generic. Okay, you see that both of them are infinite dimensional over this algebra, or infinite dimensional as vector spaces. But this one is endo-finite. This one is not endo-finite. Again, I can explain why, but you wanted to see examples of generic whether or not it exists. And a non-generic and indecomposable infinite dimensional module, which is not endo-finite. So here is example, non-example. And what is the upshot? Crowley-Bouvier proved that an algebra is tame if for any given integer d, you have finitely many generic modules of endo length d. Just pause for a second and see what is the beauty of the statement, regardless of what it characterizes. We're going to understand representation infinite algebras, namely those algebras for which the set of finite dimensional indecomposables is infinite, right? That was like rep infinite algebras where the tame wild dichotomy came to importance. So we are going to understand indecomposable modules here, but we seem to jump out of this finite dimensional world. We go inside the infinite dimensional modules in decomposables. And over there, we search for a particular type of indecomposables, which are called generic, defined as above. And we say this part is tame if for every given integer d, you have finitely many generic modules here whose endo length is d. My opinion is really outstanding because you're trying to parameterize something which is here by something which is not even there. In my opinion, that is the beauty of how they approach the dichotomy problem through the term or technique of generic modules. That said, let's go to the problems and conjectures, because without problems and conjectures, you won't even clap for me at the end. I could say, okay, we could learn all of this. So problems and conjectures, we saw this setting, all of the related problems about small indecomposables, large indecomposables, generic modules, all those questions. And now generic modules contributed to our understanding of rep finite, rep infinite, tame, and wild. The goal was understanding indecomposables of finite dimensional type. If you want to forget about whatever I said, that's a good moment, okay? You can pick up one definition and just jump on the train from now on. A module is called Schur representation if the endomorphism algebra that we alluded to earlier is one-dimensional. What does that mean? A module is Schur representation, it's called Schur representations if every non-zero A homomorphism from M to M is invertible. Note that the definition is given for modules of finite length. I said pick up one definition, but I didn't say this one. I meant this one. Okay. If you have used all your attention, I'm sorry, but erase that. So, this one. So a module without any constraints on the length, whether or not it's finite dimensional or infinite dimensional. A module is called a brick if the endomorphism algebra is a division ring. Secondly, every Schur representation is a brick, but not the converse. The example that I showed you is over this one is a brick, but it's not a Schur representation. So now a couple of quick observations. Where do bricks live? Bricks live obviously inside the indecomposables. By definition, obviously they are always indecomposables. And they're there. Here we go. And then we want to care about bricks which are finite dimensional. What are they? We call them Schur representations. It's a kind of lengthy word. So I'm going to refer to them as small bricks, large bricks. I hope it's suggestive enough. Okay. Small bricks with brick, lowercase brick, and arbitrary bricks with capital B. Okay. Now, so life became easy after people did the homework problems. We just want to make it hard again. Okay, so the question is, what type of problems could be asked about the phenomena of brick finite, brick infinite? Can an algebra here tame or wild? Can an algebra with infinitely many indecomposables be brick finite? Namely, can this family, the yellow part, be infinite, but this pink part becomes finite? Yes. How small can it be? The pink part can be as small as just 1, whereas the yellow one can be as large as being wild. Remember, wild was really crazy. X, Y, Z, subject to all relations, all, let's say, Mn equals 0, M and N being X, Y, Z, whatever you want. So this is wild. You cannot even parameterize in decomposables, but it has only 1 brick. So this is how far these two notions can get. Okay, I think I still have about 4 minutes, if I'm not mistaken. So I try to maximize the use of time and state at least the conjecture and leave the results for follow-up. The small bricks are denoted by them, and the question is, what are they good for? They are used in torsion theory, stability conditions, lattice theory, and wide subcategories and such. You are not familiar with these, forget about them. You are interested in these, come and talk to me after the talk. I'm more than happy to follow up in that direction, which is the realm that I usually think about. So our objective is to talk about the distribution of bricks now. Now that we understand, thanks to the great work of people, the distribution of indecomposables, let's torture ourselves and talk about the distribution of bricks that we don't yet understand. We saw this bunch of results, outstanding work. Let's pose similar questions. Let's be naive and try to produce naive statements from those outstanding work. What was the naive approach? We took those great statements, we replaced the word indecomposable by the word brick. Remember, brick was inside the indecomposables. Now we are going to repose the same problems about this small set. Naive change of statement. They are no longer conjectures. They are no longer statements. They're just they're no longer theorem. They're just statements as appear on the board. I've used a lot of time to give you 30 seconds to just estimate your feeling about whether or not they can be true in the first place. But I'm gonna spoil the fun and say that, well, 3 of them are immediately false. You may wonder, what are the non-examples? I'll send you back to the tame case and say, over this very simple tame algebra, you can produce non-examples for those 3 ludicrous statements. You wonder about the first one. Well, we did the same, we wondered. And 2 groups of people, myself and Charles Paquette, my collaborator, as well as Schur and Treffinger, proved that this first one holds, okay? So namely, if your algebra admits infinitely many bricks, and never go somewhere far enough and say, okay, this is the end of the story. There is no more brick. No, should go forever. Again, there is no bound on the length of bricks. Remember, bricks are particular type of, let's turn it to a valid statement, BBT1, B because of the brick property, BT because of Browthral. Now you may wonder, now that the statements were wrong, is there any correct statement one could hope for? Well, that was one thing that I started thinking about in 2019 and became part of my research for the following 3-4 years. In 2019, I stated the following conjecture, that if an algebra is brick infinite, then you can find one integer for which there are infinitely many bricks of that length. I stated as if and only if, but the other side is trivial, right? Because if you have infinitely many bricks of the same length, obviously your algebra is brick infinite. It stated if and only if, because one side of a piece of advice, a glorious piece of advice that my former master supervisor gave me is like a two-sided statement is significant if you understand one side of it very well and the other side hits you as a surprise. So one side of this statement is trivial. The other side hit me as a surprise. Okay, and it is still hitting me as a surprise. The question is, how far have we got and what contributions do they make? They make contributions to these areas. And actually, that's the setting that I began from. I didn't start thinking about the problem this way. I'm selling out my product after I have massaged it enough, so it became a simple looking problem. I started from this setting and I stated something which doesn't look familiar nor interesting to you. So I've massaged it. I've given you a little bit of motivation from some rich problems to state this conjecture. And let me be saying, I'm going to skip over a couple of slides. We were interested in that particular pinkish box. We were wondering whether or not the generic modules and this pinkish box we care about intersect. That's a very natural question. Now that you have a bunch of like subsets, do they intersect? Do they not? If they intersect, can you use them in order to understand the small bricks you're interested in? Because you're interested in bricks here. Again, can we borrow something from there? Okay, that's like a very hand-waving statement of our conjecture. With Charles Paquette, actually, we have two additional conjectures, which can be phrased in terms of continuity problem. Okay, I'll leave it aside. Terminology is pushed aside, and I'm going to finish with this. A bunch of implications of the conjectures which are not known to hold, whether or not MP2 implies MP1. MP1 implies M, but we don't know, actually nobody yet knows, that whether or not M implies MP1 and MP1 implies MP2, these are not known. But let me finish with just pictures. Like pictures do a better job. We were in the realm of rep-infinite algebras, and we divided things into two parts, tame and wide. Inside rep-infinite algebras, I know that in this room now, the next speaker hates me the most because I'm stealing time. My apologies. Inside rep-infinite algebras, there is a family which is break-infinite, okay? Among break-infinite algebras, there are tame break-infinite and wide break-infinite. If you start from tame break-infinite, over there is a bunch of algebras that are interesting. Biserial, special biserial, string algebras, gentle algebras, and such. You might have heard of them for whatever reason. Have settled the problem for biserial algebras. That's all I want to say as the conclusion. We have settled the problem, the conjecture, for biserial algebras. What do I mean by that? It states that a biserial algebra is break-infinite if and only if you can find an integer for which there are infinitely many bricks of that length. And you hope that there are infinitely many integers with that property? No, but there is always one integer with that property. You want to feel like, oh, we have listened to some good math because there were parts that we couldn't understand. Well, here is the part that you shouldn't understand, and it may kind of sell me as a smarter person, but technically these are rewarding of the question that I posed and the results we have got. They could be stated in terms of Tau-tilting theory, in terms of moduli space of representation varieties and such, but I stop here and I thank you very much for your patience. Thank you.
So we don't have much time for questions, maybe a tiny one.
The strongest conjecture, like just the generic group.
Exactly.
Okay, and is this true for biserial algebras?
Exactly. So we have proved the strongest version of the existing conjecture at the level of break-infiniteness, which states a biserial algebra, whatever that means, which could be defined, is brick infinite if and only if there is a generic brick. And that generic brick, in some cases, is only one.